Hello, young physicists. Ever wondered why your fridge magnets just stick around and never drift off? It's all thanks to something invisible but powerful: magnetic fields. Think of a magnetic field as kind of like an invisible force field that surrounds a magnet or even a current carrying wire. In this magical region of space, other magnets or moving electric charges can feel the magnetic pull or push without even touching. Now, here's a cool fact: magnetic fields are vector quantities. What does that mean? Well, they have both magnitude, which tells you how strong the field is, and direction, which points where the magnetic force acts. Scientists like to denote this with a fancy symbol, the letter B with an arrow over it. And when we measure magnetic fields, we use the unit called Tesla, abbreviated as T. 1 Tesla is defined as 1 Newton per ampere per meter. Don't worry if that sounds like a lot, just remember Tesla measures magnetic field strength, just like meters measure length. But where do these fields come from? They arise because electric charges are on the move. Either charges physically flowing in a wire or the tiny intrinsic magnetic moments of particles like electrons create these fascinating magnetic fields around them. So next time you see a magnet sticking stubbornly to metal, thank those moving charges and their magnetic fields for doing all the invisible work. Now that we know magnetic fields are invisible, how do we visualize them? That's where magnetic field lines step in. Imagine them as imaginary lines drawn around a magnet that tell us both the direction and the nature of the magnetic field. Picture a classic bar magnet. These lines zoom out from the magnet's north pole and swoop back into the south pole, looping all the way through the magnet to make continuous closed curves. So, these aren't just random doodles. At any point, if you picture a little arrow tangent to a magnetic field line, that arrow points exactly in the direction of the magnetic field vector B right there. Here's something neat. If the field lines are tightly packed together, it means the magnetic field is strong at that spot. Conversely, if the lines spread out and become sparse, the field is weak. It's a bit like the flow of cars on a highway. Lots of cars bumper to bumper mean heavy traffic or strong field, while few cars cruising far apart mean light traffic or a weaker field. These field lines are our trusty maps helping us understand how magnets talk to their surroundings without any strings attached. Let's dive deeper into these magical magnetic field lines and explore their key properties. First off, magnetic field lines never intersect. Imagine if two roads crossed in the sky and you could be on both at the same time. That would be confusing, right? Similarly, if magnetic lines crossed, that would mean two directions of the magnetic field at the same point, which is simply impossible. Also, these lines form continuous closed loops. Outside the magnet, they run from the north pole to the south pole, but wait for it inside the magnet, they loop back from south to north. So, it's like a never-ending traffic circle that keeps magnetic flux moving smoothly. The density or closeness of these lines shows us the strength of the magnetic field. More lines crowded together tell us the field is strong there. In places where the field is uniform, like inside a solenoid coil or between two magnets with like poles facing each other, these lines run parallel and stay nicely spaced. It's a bit like having well-ordered soldiers standing in rows, showing the magnetic field is steady and uniform in that region. With these properties, magnetic field lines are more than just drawings. They are the language magnets use to describe their invisible world. Now, let's look at a classic, the magnetic field created by a bar magnet. You can think of a bar magnet as a tiny magnetic dipole, a bit like a mini electric dipole with two poles, north and south. The magnetic field it produces is similar to what you'd get from a pair of equal and opposite magnetic charges separated by a small distance, except real magnetic monopoles don't exist. At certain points along the magnet's axial line, which is the line extending straight out from the poles, the magnetic field B can be calculated using a formula. B equals the permeability of free space divided by 4 pi multiplied by 2 times the magnetic moment m, then divided by the distance r cubed. Simply put, B equals mu0 over 4 pi times 2m over r cubed. Here, mu0 is a constant that represents how magnetic fields behave in a vacuum. M is the magnetic moment, a measure of how strong and oriented the magnet is, and r is the distance from the magnet's center. On the equatorial line, which is perpendicular to the axial line and passes through the center of the magnet, the field is also given by a formula. B equals mu0 over 4 pi multiplied by the magnetic moment m over r cubed. Notice here it's just m over r cubed, not 2m. Interestingly, the field's direction on the equatorial line is opposite to that on the axial line. One more thing that the formulas tell us is that the magnetic field's strength decreases with the cube of the distance from the magnet. So, if you move twice as far away, the field becomes 8 times weaker. Picture the diagram where you see a bar magnet with north and south poles labeled, arrows showing magnetic field vectors stemming out along these lines, giving you a perfect visual of this dipole field pattern. Let's put that bar magnet formula to work with a simple example. Suppose the bar magnet's magnetic moment m is 1.2 ampere meter squared, which means it has a decent magnetic strength, and you want to find the magnetic field B at a point 0.2 meters away along its axial line. Recall the formula. Magnetic field B equals the permeability of free space divided by 4 pi multiplied by 2 times the magnetic moment m divided by the distance r cubed. Substituting the numbers, mu0 over 4 pi equals 10 to the power of negative 7 times 2 times 1.2 divided by 0.2 cubed. Doing the math step by step, the denominator 0.2 cubed is 0.08, so the whole expression comes to 3 times 10 to the power of negative 5 Tesla. To put it simply, that's 30 microteslas. Just to give you some perspective, the Earth's magnetic field near the surface is about 25 to 65 microteslas, so our bar magnet's field at that distance is comparable to natural magnetic fields we live with. This tells us our answer is reasonable, and so the formula works beautifully to describe the field around dipoles like bar magnets. Switching gears from magnets to electric currents, let's explore the magnetic field formed around a current-carrying conductor. Remember Oersted's famous experiment? He discovered that a straight wire carrying electric current actually produces a magnetic field around it, which forms circular loops centered on the wire. It's as if the wire is a tiny magician, creating invisible rings of magnetism all around itself. To find which way the field goes, we use the right-hand thumb rule. Point your right thumb in the direction of current and curl your fingers around the wire. Your fingers show the direction of the magnetic field B lines. Magnificent, right? Now, the strength of this field at any point a distance r away from the wire is given by a neat formula. B equals mu0 times I divided by 2 pi r. Say that with me slowly. Magnetic field B equals mu0 multiplied by current I divided by 2 times pi times distance r. Here, I is the current flowing through the wire. The formula tells us two things: increase the current and the field gets stronger, move farther away from the wire, and the field weakens. The diagram shows us concentric circles around the straight wire, each labeled with the current I flowing along the wire and arrows demonstrating the magnetic field direction curling around, perfectly capturing this circular symmetry. Let's wrap up what we've learned about magnetic fields and their field lines. First, remember the formula for the magnetic field around a long, straight wire. Magnetic field B equals mu0 times current I divided by 2 pi times distance r. For a bar magnet's axial field, magnetic field B axial equals mu0 over 4 pi multiplied by 2 times magnetic moment m over r cubed. And on the equatorial line, magnetic field B equatorial equals mu0 over 4 pi times magnetic moment m over r cubed. These formulas capture how fields vary with distance and geometry. Field lines are our visual guideposts, showing both direction and strength. The denser the lines, the stronger the field. They always form closed loops, flowing from north to south outside magnets and back inside. And importantly, magnetic field lines never cross each other, avoiding any confusing intersections. A. In uniform magnetic fields, like inside a solenoid, the lines are parallel and evenly spaced, making for a nice neat pattern. So, magnetic fields are not just abstract math, they are fundamental to how motors spin, how compasses point, and how your headphone speakers buzz. That is it for today's concept. Remember, physics is fun when you can laugh and learn at the same time. See you in the next session.